Recording.
Okay, so let's move to our last talk of today's session. We have a pleasure to have with us Wladimir Neves. Is a professor of mathematics of Universidade Federal of Rio de Janeiro. So today his talk will be, so can you put the first slide? Yes. And Euler-Lagrangian formulation for compressible Euler equation. So thank you very much for accepting to give a talk, and you can start.
Okay, first of all, I apologize for this first slide, okay? So the main point is that it is a joint work with the colleague Christian Olvera from Unicamp, okay? And then, in fact, the friends. So, and more than that, I'd like to say thank you very much for the organizers, in particular to Juan, to kind invitation, which I accept with great pleasure, okay? So the outline of my talk will be an introduction. Then I will present the Eulerian-Lagrangian formulation for compressible Euler equations. Then I will present you some notation background, and then we show you the existence of local solution. So what is the goal of this talk? Yeah. So we present an Eulerian-Lagrangian formulation for the compressible isentropic Euler equations with general pressure law. Using this developed Lagrangian formulation, we show a short time solution, the framework of Bessel space, H beta P on the torus for beta bigger than D over P plus 1, which means that we are working with the classical solutions. We are looking for classical solutions. The proof relies on the application of the implicit function theorem on Banach space. And to our knowledge, this is the first time the Lagrangian formulation has been employed to show local existence of solutions to compressible Euler equations. Moreover, the technique developed here could be applied to Holder space, Sikov space, Sobolev space, and also Bizov space. So let's start with the compressible Euler equations. So the basic three-dimensional balance law of continuous physics in local form are the evolution equation of conservation of mass or continuity equation, the linear momentum equation, so there are three equations here, and the energy equation. So this well-known balance laws from continuous physics. In this Eulerian formulation, ρ is the density, depends on time and space, t and x. The u is the velocity vector field, capital T is the symmetric stress tensor, Q is the heat flux, B is some Bohr force, external Bohr force, little e is internal energy, R is energy supply, and the capital E denotes the internal energy plus the cinetic energy. So as you see here in the equations. Here is T, as I said before, from 0 to T for some capital T, positive, and X is in RD on the torus, and there is no boundary conditions are required. So most of the time, the U will be 2 or 3, and the U is just the tensor product of the velocity. We are interested to study the existence of solution local in time, as I said before, for elastic fluids in viscosity. It means non-viscous and non-heat conductive, which heat source in also internal force and negligence. So the stress tensor UB minus pressure identity, Q, B, and R equals 0, and P is the pressure. Then system 1, the balance laws, under assumption 2, turns into the so-called Euler equations, where the last equation 3, the last equation here in 3, usually carry the balance of internal energy, because now you have, instead of capital E, you have little e. The system 3 has too few equations for too many unknowns. Hence, in order to close the system, its suitable equations of states are needed. For instance, you may consider the pressure that depends on the density and theta, which is the thermodynamic temperature, and internal energy is also dependent on the density and the thermodynamic temperature. Moreover, in elastic fluid, the pressure and internal energy must satisfy the following Gibbs relation. This Gibbs relation is very interesting because from number 3 and number 4, which is Gibbs relation, we may write the Euler equations in a more convenient way. The first one is conservation of mass, the second one is linear momentum, and the third one is the equation for the entropy. Okay, last but not least, we call that since theta, the temperature in the density are positive, assume that the density is positive, in order to system 3 be symmetrizable, which is very important physically, you must have, I mean, the pressure should, derivative of the pressure against the density should be positive, and also the specific heat should be also positive. Then we can describe the variables in the Euler equations in terms of T and the material point A. I mean, we start to talk with the idea of Lagrangian formulation, namely Lagrange formulation. The Lagrange variables are path mappings for the material point A or key T of A and the connection between the Eulerian description and the Lagrangian one is given when the flow, T of T, is the solution for each T of the following system of differential equations. So this is the OD, which relates to the flow with the velocity vector field. We are assuming all the time at this point that we have enough regularity. So some notation when x, little x is key of the flow at some material point A. So you have the capital D of T, which is the usual material derivative, time derivative. So it should be expressed in this way for the scalar vector field phi. If for some vector field W should be written in this way, is given by this way. Also, the gradient with respect to A of the scalar field phi is given by this expression, and the gradient of W, a vector field with respect to little e, is given by this expression, where this star means the adjoint of some, M star is the adjoint of some matrix M. So this will be useful to rewrite the equations in the Lagrangian form. Thus, the Euler equations can be rewritten like the material derivative of the density equal minus whole divergence of U, whole dt of U minus gradient of the pressure, and whole dt of S is equal 0. The equation 9 expresses the fact that the change of states are adiabatic. It means the absence of heat conduction between different parts of the fluid, which means that whole dt of S equals 0. So I'm so sorry. It's become a mess. How I could turn this, I could not know how to do that. Oh, sorry.
I don't know. Control L is to turn left. So if you try.
Again? Okay.
You press the slide and
Okay, so
you just point the slide and you press Control L.
okay, thank you. So it works now. Okay, we were here on the question 9. Now we pass to this now. So if the entropy is constant, rho the volume of the fluid at some initial instant, then it remains the same constant value everywhere. Therefore, we may assume that the entropy S here in the question 9 is constant, and we do so in what follows, which means that the motion is entropic. So we are not going to consider the equation 9. Then the pressure depends just on the density. Since the pressure is dependent on the density and the entropy, for instance, since entropy is constant, now the pressure depends just on the density, and you should have P prime of rho positive. Moreover, as you have been assuming that the density is positive, we could define the enthalpy, which will be defined by h prime of rho will be prime divided by rho. It's well known in compressible fluid mechanics. Then we have dt of rho plus u dot gradient of rho plus rho divided equals 0 is continuous equation and the linear moment equation. So this is equation 10. Okay. So let me do now. I'm here. So it's very complicated there.
You can press another
Yeah.
time. So it
Yes,
will
but it's
turn
changing.
left with the one.
Yes, it works now, but unfortunately, it changed the slides. So we end up with these two equations for the system of Euler equations. And we recall that the Eulerian-Lagrangian formulation for the incompressible Euler equation was studied by Peter Constantin, okay, in 2000, and more recently by Paul Hobson, um, in the when Constantine studied in the space of whole space C1 alpha, and Paul and Hobson studied this problem in the Sobolev space HS in the torus. Okay, so but in the incompressible case, we are studying the compressible one. I should say more. In fact, this problem to the idea of Lagrange formulation to study our equation goes back to Arnold. In fact, in some geometrical infinite dimensional sets, also in the incompressible case. So let me put here and try to do what you say. Okay, it seems it works. So now let's pass into the Euler-Lagrangian formulation, okay? And first of all, we're going to introduce the back-to-labels map. So we introduce the so-called Eulerian-Lagrangian formulation for compressible equations. It will start it. Let us consider companion to system 6. What are the system 6? The OD for the flow. So companion to 6C to system 6. We consider the so-called back-to-labels map defined by A of t, capital A of t is exactly the inverse of the flow. So it means that the material point is given by the back-to-labels map applied to composed with the flow. This back-to-label map most satisfies the active vector equation. More precisely, given the vector field U, the back-to-label map is a solution of this Cauchy problem. So the material derivative of the back-to-labels map should be 0, and the initial data is the identity map. Then we introduce the idea of the virtual velocity V obtained by the solution of the Cauchy problem. So we introduce this virtual velocity, and the solution of this virtual velocity will be the composition of the initial data with the back-to-labels map. To follow, we observe that the first equation 10, the continuity equation in the Euler system, corresponds to the continuity equation written in Eulerian coordinates, which could be also written in Lagrangian coordinates. So it means that the density at some time t and point x will be the Jacobian of the back-to-labels map times the initial density composed with the back-to-labels map. Okay? Finally, the formulation comprises the following Cauchy problem. So we call the material derivative of Q should be equals capital H of Tx, where capital H of Tx is the composition of the enthalpy with the density, minus capital K, which is exactly the cinetic equation, the cinetic, a half of the velocity, a modulus of the velocity square. So since the continuous equations has already been formulated in both Eulerian and Lagrangian description, it remains to study the linear momentum equation, which is done in the following two sections. So what we're going to do now, we are going to present from how we can pass, consider the linear momentum equation, how we can pass from the Eulerian to Lagrangian, and then we show how we could pass from the Lagrangian to Eulerian in order to show that they are equivalent. So passing for the Eulerian to Lagrangian, we start with the velocity vector field u at some time t and material point A. So this will be the derivative of the flow. So you take the derivative with respect to time of the velocity. This will be the acceleration. So now you consider the linear momentum equation. So derivative of the acceleration will be minus derivative of capital H respect to xi. That could be written this way. Observe that here now you have tilde, capital H tilde, which is in fact the composition of H with the flow. Then you pre-multiply by the transpose of the gradients of the flow, and you gain this equation, okay? And then we integrate from 0 to t, and also pre-multiply by the gradient, the transpose of the gradient of t, and you have this expression. So it means that you have the velocity related to this initial time, this initial velocity, sorry, and plus this term, which can be written as this equation. So this has not been done before for compressible model, okay? Finally, making A, the material point, exactly the back to Laplace map to some point x, you obtain your equation for U written in this form, okay? Which is to say that U is given by the transpose of the gradient of the back to Laplace map applied to the virtual velocity plus the gradient of Q. So you have passed from the Eulerian formulation to Lagrangian formulation. So this is the Lagrangian formulation. Now you have to come back. So you have to show that you could obtain the Eulerian formulation for the Lagrangian formulation. Now you take the material derivative of equation 15. So you take the capital D of T of U, and then use some relations, and you end up that the material derivative of U is given by the minus of the gradient of the enthalpy composed with the density, which is exactly the second equation in your Euler system. So somehow the previous calculation leads to the conclusion that a pair of functions, ρ and u, density and velocity vector fields, satisfies the isentropic Euler equations 10 if and only if the equation 15 in Lagrangian formulation is satisfied. That is to say, so EOTX minus this expression, so this is exactly the virtual velocity with the composition of the initial velocity with the back to Laplace map, plus this term, and this should be 0. Here, you pass from the capital H to little h, and this little h is composed with the density, but you have already considered here the equation for the continuity equation in the Lagrangian form. So where you have used sorting, which is the Lagrangian formulation for the density, and AT is given by 11. Therefore, given the initial density ρ0 and the initial velocity u0, the equation above just depends on the velocity vector field u. So somehow, if you resolve this equation for u obtained by the Baxter-Labels map, you have a solution for your Euler system. Okay? So some notation background. you are going to work in the best space, H beta of P of the torus, on the torus, for beta bigger than D is dimension, divided by P plus 1. So it means that you have embedding in regular solutions. Okay, you're going to get regular solution. So just to give you some notation, but just to recall that in fact this page at H beta of P of the torus will be a distribution that is with this norm finite. Okay? So in order to resolve the equation 15, the Lagrange formulation, we are going to apply the implicit function theorem. So to apply the implicit function theorem, we are going to prescribe some map and differentiate this map with respect to U. So conveniently, we introduce this notation. So this OD, the derivative of the flow with respect to T, when the drift vector field is just U, we are going to plug U here. But now it will be important to consider the flow plus the initial flow. Okay? So we are going to use this notation to mean that the flow depends on the drift, which is U plus the initial velocity U0. And then we have this proposition. Well, first of all, I would like to say that all of these details is already submitted for publication and could be seen in archive, and I'm going to show you the archive number. Okay? So you have this proposition 1, which means that the first derivative of the flow x of t with respect to the drift u is given by this expression. Analogously, the first derivative with respect of its inverse, which is a of t, at u goes 0, is given by this expression. These two expressions will be used below. Then you pass to the main theorem, which is the local solution for the Euler system. So let beta be any real number bigger than this value with p from 1 to plus infinity. Consider the Cauchy problem associated with 10 and the initial data for the density in H b plus 1 of p of the torus and the velocity H b plus 2 of p of the torus. Then this is a local result. Then there exists a capital T positive such that equation 10 has a unique classical solution in this class of classical solution. So the density and the velocity will be C1 on 0t times RD. Oh, sorry, it's not RD, is P of D, is the torus, satisfying the initial condition. Moreover, the solutions ρ and U belong to this space. So this is the well-known theorem for classical solution, local classical solution for the Euler system. So, sorry, let me tell you that this existence for this system has been already. So, actually, it's using the Eulerian formulation. So the proof of theorem 1, this theorem, the main theorem, in its Eulerian formulation and the sublevel space HS was idemptically provided by Cato and Lax, and Peter Lax. Cato's approach relies on abstract theory of evolutionary equation, so use same group idea, non-autonomous same group idea, while the Lax method is based on the more elementary existence theory of linear symmetric hyperbolic systems with smooth coefficients. Okay, in fact, use an iterative method and apply fixed point theorem. Detailed proofs for Lax approach can be found in the books of Benzoni and Denisset, chapter 10.1, and also the nice book from Baori, Shaman, and Duncan in chapter 4.3. So the existing theory for this problem, at least in HS space, on sublevel space, was given by Kato and Lax some time ago. Our proof of the main theorem is given below. The initial step is to define an appropriate mapping for applying the implicit function theorem. Unlike the incompressible Lagrangian formulation, the compressible case exhibits a definite loss of regularity, requiring a regularization process. So when for instance, the paper from Peter Constantine, or even the other papers I cited before, when you have a loss of regularity, but when you apply the projector operator for the incompressible model, you regain the regularity. So this regularization process is not needed. We took some time to understand what we could do because we tried to follow the ideas from the incompressible case, but once we get the Lagrangian formulation, which is not so easy, we try to follow the idea from the incompressible case, but it's not possible because of this definite loss of regularity. So the proof of the main theorem. So given an initial data for the density in this space and the initial velocity in this space, fixed. So rho zero and nu zero is fixed. And then we consider the mapping f from 0 plus infinity times h beta p on the torus to h beta minus 2 of p on the torus. So this mapping is defined almost the same like the equation 15, I mean the Lagrangian formulation, but now, as I said before, instead of u, we are using u plus u0. So this is the mapping for the implicit function theorem to apply the fixed point theorem. Or equivalently, we may write this mapping in this way. It's not difficult to see that, where a of t u plus u0 is the inverse of the flow defined in equation 15, as I showed before, and capital J denotes the Jacobian of the flow. Why use u plus u0 instead of u? Because it's so simple. I mean, you observe that the mapping above is clearly equivalent to the equation 15, as I said before, but the field u there is replaced here conveniently by u plus u0, which is to say u equals 0 here corresponds to let u equal the initial data u0 in the formulation 15. This is motivated by the application of the implicit function theorem. What I'd like to say, indeed, it follows that we consider the point to apply the fixed point. We are considering the initial point, the time t equals 0, and the u equals 0. So it's easy to see that you're mapping capital F at point time 0 and u0 goes 0 trivially. So you have f of 0, 0 goes 0 trivially. Moreover, it's not difficult to show that f is a continuous difference mapping, considering in particular proposition 1. So you have to differentiate your mapping f with respect to the second component, which is u, and you have to use the proposition 1. Okay? So to apply the implicit function theorem, it's also important to show that the differential of f in respect to u, the second component, at point 0, 0, is a linear homeomorphism from h beta p onto h beta p minus 2. Then you consider the following claim. So when you differentiate, when you get the differential derivative of f at 0, 0, at some applied to some vector field w, this gives you exactly the vector field w, which means that is the density mapping. So the differential derivative of f at 0, 0 is the identity mapping. So since you have this derivative, the identity, we have a loss of regularity, that is, d of u of 0 f at point 0, 0 is the identity mapping from h beta of p on h beta minus 2 of p. So you could not have the inverse of the map with this regularity, not gain the regularity. He gained the regularity. How could you resolve this? To overcome this difficult, you apply a regularization procedure. We are going to regularize in space. Okay? So somehow this looks like the Nash-Moser idea. So let capital S of T be the heat semigroup. Then for each epsilon positive sufficiently small, we define the mapping. So F epsilon from 0 infinity times h beta p, now to h beta p, the same space, where f epsilon of tu is defined as f of t of u epsilon, where u epsilon exactly is the regularization procedure given by your semigroup idea. So f epsilon of t of u is given by f, as I showed you before, at point t and s epsilon of u. Yes, whereas epsilon of u is u epsilon is s epsilon of u, and f is defined as above. Remark that the regularization procedure is just in the space variable. Then we apply the implicit function theorem. Then you try to apply the fixed function theorem again. Again, we clearly have f epsilon at point time t goes 0 and u goes 0 is 0. And similarly, we again, as declared above, you obtain the first derivative of your function capital F of epsilon at the point 0, 0 applied to vector W is the vector W regularized. So it means that where the W epsilon is just your semigroup applied to the vector field W. So we regularize the vector field U, and you take this derivative at this point, you get this. Now, since you have used the regularization, yeah, you observe that F epsilon could be written as identity minus identity minus S epsilon, and using that the epsilon, capital S epsilon minus identity goes to 0 in this norm as epsilon goes to 0, there exists some epsilon naught positive such that S epsilon naught minus identity is less than 1. So it means that then we deduce that S epsilon from this space is an invertible operator, and thus the Frechet derivative of the map F epsilon 0 or F epsilon naught at these points is a linear homeomorphism from this space to this space. So then you have F epsilon 0, 0 is 0. You have the derivative, the first derivative of F epsilon 0 at the point t goes 0, u goes 0, is a linear homeomorphism from this space to this space. And then to apply the implicit function theorem, it remains to show that F epsilon is well defined. Then you consider the claim number 2. So you claim that for each t positive, non-negative, and u in this class, F epsilon is finite. The proof of this theorem falls since this space for beta bigger than d of p plus 1 is an algebra, and also that they are invariant under diffeomorphism. So it's not so difficult with this condition for beta to show that in fact this capital F epsilon is well defined. Epsilon could be here F epsilon 0. Then we apply the implicit function theorem, and you obtain some capital T and a ball from 0 to this capital T, where for each t in this interval, I should say, E of t is the unique solution and it has this class. That means that E of t, E will be in this class. So it means that the proof of the main theorem is finished. As I said before, all of details of this paper, I mean this talk, could be seen in the archive. You could be seen, and then I'd like to say thank you very much for your attention. Okay.
Okay, thank you very much, Wladimir, for this talk. So let's ask the audience if there are any questions or comments.
Okay.
Okay. So as usual, you can use your microphones. I think Juan will, yes, will open the microphone for the, okay.
So, and I should say thank you very much for your help concerning this rotation of the.
Okay,
I
don't
appreciate so
worry.
much. Thank
Just
you very
some
much.
technical issues.
Yes.
Are there
Yeah.
any
Sure.
questions? While people are thinking, I have one curiosity. Is the
Yeah.
parameter beta that appears in your result, is it optimal parameter or just some sufficient condition for
You see that beta should be bigger than the dimension divided by b, plus one. So it means that all the time we are considering that the solutions are classical. So this is a local result, and the solutions are classical. I mean, the minimal beta should satisfy this. So it means that your solution is at least C1, and then you could resolve. I mean, classically the Euler system, like in the result from Cato or Peter Rax, where S should be bigger than D divided by 2 plus 1.
Yeah, related to the dimension. Okay.
Yeah.
Okay, thank you very much. Are there other questions or comments? So if not, we thank you again for this participation. Thank you very much for being with us. So
Okay.
today we finish